All right, so let's round out Unit 4 with a discussion of solids and some information in Chapter 12. There's a lot of extra information in Chapter 12 that we're not going to talk about, but it's a good idea to read over just to have some exposure to it, getting into a lot of applications of, what can you do with the understanding of these different strengths of intermolecular forces with different bonding types, varying the structure of, taking, from simple pure compounds to, making mixtures, making alloys, making polymers. That gets into like materials engineering and how do you manipulate, or materials chemistry, how do you manipulate these different bond types and these different scenarios into making materials that have different properties. So that's what chapter 12 gets into, and we don't need to go that far, but we'll touch on some of the finer points that we need to be aware of moving forward. So on the screen right now, we've got the 4 different classifications of crystalline solids, and we've got metallic solids, ionic solids, covalent network solids, and molecular solids. So you can see the different depictions, and we're going to go through what the differences are. So for the metallic solids, we are looking at metal atoms at our lattice points. So usually it's metal atoms of one particular type. We're talking about a pure metallic solid. If you're looking at alloys, though, you'd have the same idea, just with either other atoms of metal substituted in, or smaller atoms stuck in between the empty spaces. And we'll talk about those alloys again in a couple slides. We got ionic solids, which have cations and anions, which we know are held together by mutual attractions. And again, in the metallic solids, I should go back to mention that delocalized electrons. So we know that metals conduct electricity because they have that ability to pass the electrons along from one atom to another. We talk about the sea of electrons, and whether you describe it using molecular orbital theory or using the sea of electrons description. It's the same kind of idea, that there's a freedom of movement of electrons in the metals themselves, and therefore it allows an electric current or heat energy to be transferred easily throughout the structure as well. We don't see that happening with ionic solids, so our particles are very tightly held in place because you have the positive and the negative alternating pattern. And so we don't see that same conductivity like we do in metallic solids with ionic. And again, because the electrons have been completely transferred over to the anion and lost from the cation, and therefore they're bound up with the anion, not free to move throughout the structure. Our other 2 solids, we have the covalent network solids. So that is atoms that are at each lattice point that are repeating throughout, but they're held together by covalent bonds. And so we see covalent network solids such as carbon in its allotropic form. So we have graphite, we have diamond. Those are or silicon, quartz, which is SiO2, just a repeating structure of Si and O2. So those are very, very, very strong, very high melting point substances. Because if you think about what we said, molecular substances are held together by, so that's our third one. We've got these discrete molecules like you can see here. We've got the water molecules packed into the crystal. It's that molecule that, although there are covalent bonds present, what's holding them in place in a solid is their attractions for the other neighboring molecules, which is our van der Waals forces, our intermolecular forces. So, and in comparing these two, they both have covalent bonds in them, but the covalent network, or the macromolecular solids, have covalent bonds holding together each of the lattice points, and that makes it a very, very strong structure, because that means breaking those bonds if you're going to separate the lattice points, versus these molecular solids, which are a lot of these substances we've talked about already, HBr, H2O, that again, they are attracted to each other by those intermolecular forces, and once those are overcome, which is a lot easier to do and a lot less energy to do than breaking covalent bonds, we'll see that those have, again, their properties are reflected in being a lot weaker, lower boiling points, lower melting points, etc., for those versus the covalent network. Likewise, if we compare molecular solids to ionic and metallic, again, ionic bonds, metallic bonds, those are considered to be intramolecular forces, just like covalent bonds. So that's why we're going to see molecular solids with the lowest boiling points, melting points, well, lowest melting points if we're talking about solids, in comparison to metallic and ionic, because we're talking about only overcoming intermolecular and not the intramolecular bonding forces. Hello, so just want to show you a couple of visuals of what I was just talking about. So obviously we've got, keep seeing the ionic solid, and I've showed you this in class. So we've got the alternating positive and negative are attracted to each other and very rigidly held in place. When we compare that to the, so this is a molecular solid, so this is looking at the water molecules. So each water molecule, that's the repeating unit that we see throughout the structure, and it's just the attractions. So in this case with water, we know it's hydrogen bonding, just the attractions of the partially negative end of one water molecule to the partially positive end of another water molecule that then holds together the molecules in a solid. So that's a lot weaker than the ionic bonds. If we look at the diamond structure, so if we think about what each carbon is going through, notice this carbon right here. So it's got a tetrahedral bond or tetrahedral shape with the atoms it's attached to. So we just focus on this one. Notice we've got bonded to, with covalent bonds, 4 other carbons. Then this carbon that it's bonded to is bonded to 4 other carbons, and 3 other carbons, and so forth. And so that's where we get this network. And that's the case with all of our macromolecular or covalent network solids. And so again, when we look at the melting points of these kind of solids, it's actually usually a decomposition point instead of a melting point, because melting would imply that we can loosen these attractions enough to allow the particles to slide past each other. That's just not going to happen if you've got, these are covalent bonds. So to overcome this, you're literally breaking the bond. And so anyway, we kind of more see these decompose at very high temperatures rather than melting. So anyway, that's kind of what that would look like put together versus the, again, it's molecules that are repeating over and over again versus atoms that have covalent bonds holding them together. I don't have a metallic solid example, but anyway, you get the idea. Next thing we're going to take a look at is the 2 different types of solid arrangement. So these solids that I've just shown you, although this looks like a big mess, if I had more atoms, this would be a nice big network, and you can see a picture of that on the slides and in the book. But notice ordered arrangement, whatever it is. When I keep saying the unit cell, it's whatever unit keeps repeating throughout. So in our crystal, so ionic compounds are considered crystalline solids. Our molecular, and this repeating pattern of these molecules are repeating throughout the structure. And then in molecular solids, we've got this repeating pattern. Same thing with metallic. But when we look at something like plastics, you know, plastic wrap. And the most annoying thing about plastic wrap, if you buy a cheap plastic wrap, is being able to tear it straight. And I can't even look, it's all stuck here. You can do it. So if you don't have this lovely little serrated edge to help you with your cutting, what happens? Well, oh, it's not working. Tear. What's your problem? Look at that. So we know that plastics do this, right? So we have this uneven ripping, the stretching. We've seen plastics, like when you get them warm, they're not quite melted yet, but they kind of soften and they're easier to stretch. Hello. So the deal with plastics is they're not like these other solids. They're not crystalline solids. They are what we call amorphous solids. So let's switch back to the slide presentation so you don't have to keep watching me bumble around. Okay, so here's 2 examples of what I was just talking about. So the crystalline solids are the 4 different solid types that we already talked about, and that means there's a arranged, very regular pattern. Something like plastic has the amorphous, so amorphous meaning without shape. Now, we know that solids have shapes, so, you know, certainly that piece of plastic wrap I was holding up has a shape. You know, if I have a plastic marker or plastic cup, it has a shape, but the arrangement of the particles is not ordered and patterned like a crystalline solid. So that's really the difference. And we do see the characteristics that I mentioned. So the fact that it tears with jagged edges, the fact that it softens, amorphous solids will soften when heated, but not quite heated to their melting point, and characteristics like that. So again, it's because of that lack of structure that we see those properties. So we should be aware that there's an amorphous solid, which is a different type of structure, meaning it's not that ordered arrangement of particles like we've talked about with all the other solids before. All right, so we've talked about alloys before, so we'll just really quickly review that again. So alloys are combinations of two or more elements, majority of which are metals. So here's just some breakdown of some common alloys. Typically, if it's a solid mixture, homogeneous mixture, there can be some heterogeneous alloys, but for the most part, when we say alloy, we're talking about these homogeneous mixtures. They melt down the metals, mix them together. Because we're talking about a homogeneous mixture, notice that there's varying proportions for the metal, so it's not always the same. You can vary it. Now, typically, to get a certain set of properties, which is why you would bother to make an alloy, it can strengthen a metal, or it can, give a certain sound quality if you're looking to make bells or instruments or whatever. But anyway, certain percentages are good for producing certain strengths or certain characteristics. So again, adding any number of elements can change the properties, and changing the percentages can change the properties that the original metal would exhibit on its own. So we've got our two types of alloys that we should know, and that is substitutional versus interstitial. So in the substitutional alloy, we're literally substituting in. So instead of every atom in the structure being gold, we've got some silver atoms substituted in. And so typically for substitutional, it's got to be a similarly sized metal atom. Usually it's metal atoms. For interstitial, so interstitial, which is referring to the spaces in between the metal atoms, usually the second element is a smaller type atom and will fit like in those little nooks. If you have a bunch of spheres packed on each other, there's some empty spaces between them where the spheres don't quite meet up. So if the smaller atom can fit in there, that can actually help to improve the strength of the material quite significantly. In particular, usually there's nonmetals put in. So like in the case of steel, it's carbon, does a little bit of covalent bonding, and then again tightens up and strengthens the structure of the metal. So again, just being able to differentiate between the two types of alloys, I think, is a good thing for us, knowing what those two different terms mean. There are also in the book mentioned about heterogeneous alloys, and also regarding intermetallic compounds, which we saw an example of on the last test. And basically it's, instead of being a homogeneous mixture where you have a varying amount, you actually always have the same ratio of a certain two of this type of metal atom and one of this, and that's the repeating structure. So you can also have those as well, that kind of are similar to alloys, with again a different characteristic property than the original metals themselves, but those still exhibit more metallic character than if we were comparing that to an ionic compound or something. All right, so for metallic bonding, the atoms of nonmetals and metalloids, they'll bond with each other covalently. So we've seen any number of examples where we look at all the diatomics that do that. We've seen we talked about the macromolecular silicon or carbon, and when we get to metals, though, they tend to just kind of be content bonding with each other. And when we look at how strong the attractions are between metals in a metal solid, it's too strong to just be the same exact thing as a dispersion force, and but it's not quite the same thing as a covalent bond, because we're talking about large groups of atoms that participate in this metallic bonding together. So it's not like the discrete intervals of like a Cl2, where we've got two chlorine atoms, and then if they of course happen to be cooled down enough, they stick together. It's not like that. This is a very, very strong and a whole bunch of metal atoms together. So we usually describe this as, we have the metal cations, the valence electrons are kind of allowed to move freely throughout the group of atoms together, and we refer to this as electrons being delocalized, meaning they're not local, just belonging to one atom, but they move throughout the structure of all of the metal atoms together. And this is usually what we use to explain the electrical and thermal conductivity, ductility, malleability, all that good stuff that we usually see with metals. Which gives them the ability to be so flexible, and again, electrons can shift through. We can see that's why electricity is easily conducted. There's a description in your book, Bringing Back Molecular Orbital Theory, which helps to explain. Again, you can read through that and look at the depictions, but as you get to a series of more and more atoms, so again, metal atoms tend to do this in large groups. So looking at how the individual atomic orbitals, their wavelengths of the electrons in those orbitals would add together either constructively or destructively, and would give you these two molecular orbitals. The more atoms that are joined together, though, the more these bands of energy start to kind of creep closer together in energy, and produces kind of this huge band, it's described as, of orbitals where the electrons can go. So in the explanation under molecular orbital theory is when we have a huge amount of metallic atoms together, there's kind of this band of molecular orbitals that, let's say if I were to apply a current or an outside disturbance, then that allows electrons to kind of jump up to that molecular orbital and be transferred or pass easily throughout the structure. And so that's, again, the idea for the molecular orbital approach to describing metallic bonding. And I think mostly if you can reference the sea of electrons, delocalized electron approach, that's adequate for now. But again, more research is being done with the molecular orbital approach as we speak, like right this second. Someone's looking at it somewhere, and they'll let us know more. All right, so ionic solids, very high melting points, very high boiling points. Those are quintessential crystals, so that very ordered pattern of arrangement. So we've already talked about those. We can see the attractions between neighboring ions of opposite charge causing the strength of the structure. If we look at the effect of shifting the ions, we see where that brittleness comes from, where these two negatives come in contact, two positives, and it's going to repel itself apart. So again, that's all stuff that we've talked about with ionic. Chapter 12 goes through a lot of explanation about the different shapes, different types of lattices, and that's all based on how the ions can pack together, is all based on maximizing the contact between oppositely charged ions. So we don't need to have this memorized or anything. It's nice to take a look at in the book. Again, some information about molecular solids. So these are discrete individual molecules, so like benzene or toluene or phenol, these examples here. So these are molecules that, again, if benzene gets near another benzene molecule, it will attract to it due to just intermolecular forces, or toluene will attract to another toluene molecule just due to its intermolecular forces, or its van der Waals forces. And so, again, these units, these molecules, whatever the molecule may be, would be what's the alternating pattern repeating throughout the crystal. There's a picture of diamond, a lot better than the molecule I tried to build. So, again, you can see that tetrahedral arrangement around each carbon atom, and it just keeps continuing on and on. And that's why these molecular solids, covalent network solids, tend to have very, very high melting points. We also call them macromolecular solids, but again, it's really more of a decomposition point where it's just going to start breaking up those bonds and loosen the atoms, or free the atoms from the bonds. Graphite is an allotrope of carbon, and because it's got a layered effect, which we have that over here. So notice that graphite, which we like put in pencils, this actually, this bonding here, those are all covalent bonds, but they're actually kind of in sheets that are attracted to each other via van der Waals forces. So that's why we do notice, like graphite, you certainly have all broken pencil lead. You're certainly not going to break a diamond, because those are all covalent bonds holding things together. But with graphite, we've got just these attractions between these sheets. So these sheets are very strongly held, to each other, making up the sheets themselves. They're strongly held together, but one sheet to the next is just held together by van der Waals forces. So this actually is softer and has a lower melting point, but still has that covalent network or macromolecular solid structure we talked about. It's just constructed a little bit differently so that every atom is not directly covalently bonded to another atom. Some of these in the structure are just attracted. All right, so polymers, nanomaterials, you can read on to that, but again, we'll actually at the end of the year look at polymers a little bit. But for now, just looking at the different types of crystalline solids, knowing what an amorphous solid is, knowing what the different types of alloys are, so the interstitial and the substitutional. Those are the main points you need to come away with from chapter 12. And again, the stronger the attractive forces in the solid, the reflection we'll see in the melting points of the solid. So higher melting points for stronger forces, whatever those may be, whether it be ionic bonds holding together the lattice points, whether it be metallic bonds holding together the lattice points, covalent bonds holding together the lattice points, or van der Waals forces holding together the lattice points.